Okay, good afternoon. We start today's lesson. This lesson is a very long one, so it probably takes some sessions to complete it. The reason it is long is because I want to teach every detail around this, which is included in the book. But the final message is very easy. There is a function, we want to find its derivative. So, if you are interested to know where these things are coming from, these sessions are for it. But if you are not very interested in those things, these sessions probably will be a little bit boring for you, because the message at the end is just we want to find the derivative of a function. And this function is an exponential function. Okay? So that is the topic of the lesson. Let me remind you, what do I mean? So far, if you remember, we had, if I give you x to a power a, where a is fixed, a constant. If I give you this function, let me say this is g of x. If I ask you what the derivative is, you know the answer. So the answer is a goes down, x to power a minus 1. This function is called a power function. Okay, so if I ask you which type of function so far we know its derivative, mainly a power function. So if I have a power function, we know the derivative is a x to power a minus 1. But today we want to talk about another important type of functions that are ubiquitous in all mathematics, and that is the exponential function. Exponential is the function in which these two are flipped. Okay, so today we want to talk about this. F of x is equal to a to power x. This is not the same function as before. Here the base is variable, the exponent is constant. It's called a power function. Today we want to talk about the derivative of this function in which the base is a constant, but x is a variable. And that is called an exponential function. But there are some technicalities going on. First of all, we exclude 1 from a, because if a is 1, 1 to power x is just a constant function. It's not an exponential function. So a shouldn't be equal to 1. On the other hand, we exclude negative numbers. The reason that we exclude negative numbers is that if I let negative numbers in, then I will have problems with the domain of my function. For example, if I choose a to be minus 2, and then if I write minus 2 to power x, the point is that the domain of this function is not a continuous interval of r. For example, so this function is defined when I give you x equals to 0. It is when I put x equals to 0, x equal to 0 minus 2 to power 0 is 1, so no problems. If I give you x equals to 1, still we do not have any problems. Minus 2 to power 1 is 1, but suddenly the value in between I will face problems. For example, if I choose x to be 1/2, then suddenly this becomes undefined, because minus 2 to power 1/2 is the square root of 2, is the square root of minus 2, which is not defined. So if I want to allow the negative numbers to come in, then I have a very big problem with the numbers that I can choose for x and the numbers that I cannot choose for x. So for this one, when they talk about exponential functions in mathematics, they are implicitly assuming that a is not 1 and a is not negative. Okay, so when I say an exponential function from now on, I mean a function of this type, so that the base is a constant other than 1 and positive, and the exponent is x. The main topic of lesson, which will last several sessions, 2 sessions at least, is what is the derivative of this function. So we want to calculate the derivative of this function. Okay, the point is, first of all, I want you to feel the difference, why the problem is different. Let us go back to see what is the definition of the derivative for this function. If I ask you calculate the derivative of this function, we did it before. So this becomes the limit of g of x plus h minus g of x over h goes to 0. But if I ask you how can I calculate this limit, you go back to your function, you replace x, which is your input, with x plus h, then it becomes x plus h to power a minus g of x is x to power a divided by h. If you remember, we were not able to calculate this limit. Let me close the door. Thank you very much. Okay, so here, this is the function, but of course, if you remember, I was not able to calculate this limit for you. The only thing that I did for you is try to motivate you by considering some simple cases for A. And then I told you, okay, you need to trust me that this will work. But I mean that problem was also hard. So we didn't do it in complete form. But anyway, that is not my point here. My point is to understand why this problem is different from that problem, yes? So this is the limit, and okay, we doubtfully calculated something, and at the end we got this result. Now let me write the same thing for f of x. If I ask you what is f prime of x, which is my starting point, when you don't know the derivative of the function and you want to discover the derivative, there is only one starting point, and that is the definition of the derivative, yes? So I write f prime of x, so I will write the definition, because I don't know the derivative yet. Sorry, f of x divided by h goes to 0. And then this time, so what happens here? This becomes the limit f of x plus h. It means that I have to go to my function. This is my input. Replace the input with x plus h. Then I will get a to power x plus h. And then minus a to power x, because f of x is this function. At least you can see, now you can feel the difference, yes? In the previous case, I had to calculate this limit. In the new case, I have to calculate this limit. So that is the source of difference, at least. You can feel the difference. Okay, but the point is that if I want to calculate this limit, that's a different story. So the journey is to calculate this limit. So what we do first, I will calculate this in this form. Instead of a to power x plus h, I can decompose it by writing it as a to power h times a to power x. Or let me write it the other way around, as usual. So x, h, minus a to power x divided by h goes to 0. Okay, no problem so far. So what I have done is just I have decomposed this in that form. That is reasonable, because if I multiply these two, the bases are the same. I add the exponents. But now between these two, I can factor a to power x out. And I write it, instead of putting pair of brackets, I wrote it in this form. I put a dot here, and then I would write a to power h minus 1 divided by h goes to 0. Is that understandable so far? Yes? Okay, but now let us go back to this limit. This part is constant as far as this limit is concerned, because it depends on two things, a, which I assume is a constant from the beginning, and x is the variable, of course, but not for this limit. In this limit, I am not touching x. I am sending h to 0. So as far as this limit is concerned, a to the power of x is a constant. Okay? But this part, no. You see, this part depends on the value of h, which is the limit, which is the variable in my limit. So what I'm trying to say is that I can pull this out because that's a constant. So then I can write it as a to power x multiplied by the limit of a to power h minus 1 over h goes to 0. Yes? But the point is that calculating this limit is not as simple as usual. Okay? the whole lesson will be how to try to calculate this limit. Because if I know this limit, then I am done. For example, if this limit is 5, for example, then 5 times a to power x is my limit. But something very strange and something very interesting happens. This, at the end of the day, is a number. I still don't know that number. Okay, this is not the number among the numbers that you know. We have to understand this number as well. But let me call it L. L is the value of this limit, is still missing for us. But then, assuming that I calculated this limit and it becomes L, I multiply it here. It becomes L multiplied by a to power x. So that is a very simple idea that I got. So one thing I was able to do is to show that if f of x is a to power x, then the derivative is the same function multiplied by a constant. So L times a to power x, where L is equal to the limit of a to power h minus 1 over h goes to 0. So this is the take-home lesson for the time being. And this is interesting, by the way, because in the previous case, when I have a function, when I differentiate it, of course it becomes a constant, but not a constant multiplied by the function itself. The function was x to power a. After differentiation, I have a constant, but I do not have the same function back. I have x to power 1 unit less. But that is very interesting for this function. If I start with this type of functions, when I differentiate, I get the same function, technically, up to a multiplicative constant. So that constant is this limit, and the big problem in front of us is to calculate this limit. And the bad news is that if I want to treat it very carefully, we cannot do it at this level. But I will try to justify it as much as I can. And this is also included in the book, by the way. Yes, please.
Doesn't that function approach negative infinity?
No, because when I send h to 0, the denominator vanishes, becomes very small, negligible. A to power 0 is approximately 1, very close to 1. So 1 minus 1 is also very close to 0. So it is 0 over 0. But that's a good question. This is undeterminate. Yes, you are right. If this is a number divided by 0, then it becomes a huge number. But this is also getting a small when I send h to 0. This is also small. That was a good question. Let me just address this. Because if I want to calculate this limit, I am making h smaller and smaller. When I am making h smaller and smaller, the denominator becomes smaller and smaller. But unfortunately, at the same time, the numerator is also becoming smaller and smaller. So because when h is very close to 0, a to power h is very close to 1, and then this difference is negligible again. So I am dividing an infinitesimal by an infinitesimal, which is undeterminate. So we cannot be sure that this blows up. And it does not blow up, actually. It's not a big number. So we will understand this later. So this I want you to understand. For the time being, I started with a function. I calculated the derivative. I know the general form of the derivative, except I don't know exactly the value of this constant. But I know the value of this constant is the value of this limit. If I can manage to find this, then I am done. I know the derivative in full detail. Okay? Is everything clear? Okay. Now the point is, of course, we want to understand this limit a little bit. But at this level, I cannot start teaching how to do this because it needs more advanced limit theorems. But the book is doing it, I think, they are doing a good thing here. So let us try to understand that limit. So what they do, I need my notes here because I have done the calculation using the calculator. I don't want to spend so much time on it. Okay, so what they are doing, they are setting up two tables. So to understand the problem, let us consider two particular cases. One case, let us take a to be 2, and then let us see how this limit works. Yes? Let us understand this. And once more, let me take a to be 3, and then replace a with 3 this time. H goes to 0. Let us see what can I say about these two. So the point is that I want to calculate that limit for any positive non-equal to 1 numbers, okay? But then let us say, okay, that problem is a hard problem. Let us understand the problem by calculating 2 specific values for a, choosing 2 specific values. 1, I replace that a with 2, this becomes this limit. I replace that a in this limit with 3, this becomes, okay. Now, of course, we cannot calculate them. Yes, because we don't know how to calculate them. But how, I want to test your understanding, how you get a feeling about this number. This you need to know. For example, if you want to see around which number this limit is, not exactly, approximately, what do you do? Can you tell me? Because if you want to see, if of course you can calculate the limit exactly, you do it. But in this case, we don't know. But still, we do not want to give up. We want to say something. We want to understand, for example, is it reasonable to say that this limit is 1 million? This is the one. Is it reasonable to say that this limit is around 1? Is it reasonable to say that this limit is around 3? How do you answer this question? You have a calculator. That's not hard. What do you do?
Just like plot, or if your calculator can plot graphs.
One way is to plot graphs, or if,
do it manually.
yeah, manually. This is the way that I have done it here. So I have done H. I start with numbers close to 0. And then I have started, for example, for 0.1. And I have the numbers already calculated and put them in front of me here. So when I calculate 2h minus 1 over h, so I take my calculator, I type this in with h, this value, I calculate, I get this number up to some decimal points. This is the number that I get, and I will do the same thing exactly for the other one. And when I calculate this function for this value, chosen value, I got 1.1612. And then I slowly make myself closer and closer to 0. For example, the next number that I have chosen is 0.01. And when I calculated the values are these, if I haven't done any mistakes. Hopefully not. This is one number that I get for this function, and this is one number that I get for this function. Yes? And then you realize there are not a good pattern going on, and you will realize later why you cannot see the pattern. And then I still continue a little bit more, be patient, so I will go here, and then I will get 0.6934. And for this one, I get 1.0992. And finally, I am also going one step more by going to this even closer number to 0. And I calculate it is 0.693. And the next number is 2. And this one here, I have 1.0987. Okay. I am not expecting that you guess this number, but I think you are really already understand that 1 million is a really bad guess for this, because these numbers are around this. So what is this? What this calculation is showing you? You see this digit is not stable here, but this digit becomes stable at 6. Yes, so you should expect that even if I get closer, I will not touch this decimal point. And then which one is more stable? 9 is stable here, and 3 is also stable. Okay, but let us keep 2 decimal points. So one thing is clear. These two I can rely on. They are significant figures for this limit. And what are significant figures for that limit? It's 1 point something, and you see that which ones are stable. So I would say 1.09. It seems to be stable. But my point is something. I hope that I could convince you. If you're not convinced, you can continue a little bit more. And then, by the way, writing a code like in Python, for example, generating these numbers are extremely simple. I think even GeoGebra can do something like that, but I don't know the syntax. But anyway, what I want you to understand, this is my goal, to try to show you or convince you that this limit, whatever it is, first of all, I cannot guess the exact value. And the second thing is that this is a smaller than 1. Are you happy with what I have written here? According to this calculation, if you think you are not that convinced, you can continue a little bit more, but hopefully you realize this limit is less than 1. But what that is, I don't know. And if I ask you what this limit is, I hope that you agree with me, this is greater than 1. But which value, I don't know. Yes? This is the only thing that I wanted to convince you using this table. Hopefully I succeeded. But there is a natural question coming in now. A natural question coming in. What is the natural question? I don't know. For me it was natural. Might be it's not that natural for you. So you see the limit. So my goal is to calculate this limit. I chose one specific case, and I realized that corresponding limit is less than 1. I chose another particular case. I realized that limit for that number is larger than 1.
When does it change? Like, where is the switch between greater and smaller than 1?
So what does it mean? Switch means
Or
it
like-
becomes exactly
Exactly.
1. You see, that is natural. If it's natural for you, I mean, that if you think that the way that the mathematicians think is like this, okay? So you calculate this is smaller than 1, this is greater than 1. The question might arise, okay, when it becomes 1. It's just a mathematical curiosity, okay? And then this introduces a new number in whole mathematics called Euler number. Okay, so what I'm saying is that the question is that, motivated by this is the question I ask myself. Question: is there any real number? Is there any positive real number other than 1 such that the limit, the corresponding limit for that number becomes 1? Becomes exactly 1. This is the question that comes to mind. And then the proof, the existence of such a number is again beyond the scope of this lesson. Mathematicians show that that's yes, the answer to this question is yes. And then you ask, okay, which number is that number? They don't answer you perfectly. They say that number, we call it E. Okay, so I would say that the answer to this question turns out to be yes. To be positive. And the particular, and that number is denoted by E, and is called the Euler number. Okay? So, the only thing that I am not making it complete is to prove the existence of such a number. We have to guarantee, if you're a mathematician, it's not convincing, even though intuitively it seems right. You can start playing around with those numbers so that it fine-tunes this limit exactly to be 1, but this is just a feeling. Mathematics doesn't care about our feelings, yes? It cares about what is precise. So that is what I'm saying, yes?
So that means, according to our thing up there, that E is its own derivative. Like, if
Yes, if that number is E, then the derivative is itself.
Yeah.
That is what you want to conclude. Yes, exactly. But we will come back to that later. So this E is one of the most fundamental constants in whole mathematics, like pi. Yes, so pi is so important that we reserve this letter symbol for it. And of course, if I ask you, do you know approximately pi? Hopefully you remember some parts of it. What is that? 3.14. I remember. I also remember the next one because it is simple. It is 15. 3.1415. But anyway, so that is approximately. Okay? But then I want to have something like this, some kind of estimate for E. That's also a reasonable question. Okay, this number is mysterious. You're trying to sell it to us, Babak. Okay, you're forcing us to buy it, but at least give me what is the value approximately. Okay, so we want to answer this question before continuing to the notion of the derivative. We want to understand a little bit of E. First of all, if I ask you what is E, E is this sentence, is the content of this sentence. It means that if I change A to E, I still don't know what E is, but we know this is the definition. Okay, what is the answer? Can you tell me? 1. If someone asks you why, we consider this the definition of the Euler number. It's one possible way to define the Euler number. Extremely important. Okay? Now, before continuing with our main task, which is the derivative, let us understand a little bit more about E. In other words, I want to find 2 decimal points of E. And why I'm saying 2 decimal points, because I hope that you know that this pi is an irrational number. So it means that the decimal points will never ever stop. And then that is also a mathematical theorem that this number is also an irrational number. These are just information I am passing to you, okay? All of them are theorems. So I want you to know that, first of all, E is irrational. So you cannot write this as a fraction. You have to write it as a decimal point, and the decimals continue forever. This needs proof, but that is beyond the scope of this course. But now tell me, I want to ask you, if you want to give me 2 decimal points, 3 decimal points of E, what do you do? This you should be able to answer. I'm going to clean the board. You can think. Okay, so my question is that I want to get some approximation for E. Can you help me to do that? Or tell me what to do? Yes?
We take, instead of A to be 2 or 3, we take a number between A and 2, 2 and 3, so like 2.5.
No, but how should I know? Because I won't know. That is, it's a good idea, but it's a really rough estimate. I cannot rely on those numbers that I can calculate like this. It's not a good way. No, if you want to know something about a number, you should start from its definition. So the definition of the Euler number is the unique number. By the way, uniqueness is also a theorem. So why that number is only this one? So existence of such a number and uniqueness of the number are the problems the mathematicians get money for it to solve. Yes, so that's the problem. Okay, so if you want to understand the problem, you want to know how much is approximately this E, or let me change this to approximately. But I want to rely, for example, it doesn't matter how much I go in decimal points, these digits are not changed. They are reliable. So I want to find some reliable values for e as well. So I would say that, okay, when you say this limit e to power h minus 1 over h goes to 0 is exactly 1, this is my starting point. This means that e to power h minus 1 over h is approximately 1. But this approximation becomes better and better whenever h is smaller and smaller. Okay, so this is important. This approximation becomes better and better when h becomes smaller and smaller. Whenever h becomes closer and closer to 0. Okay, so that is what we know. But before starting doing calculations, let me just try to do some algebra. E to power h minus 1 over h is approximately equal to 1. I multiply everything by h. Then it means e to power h minus 1 is approximately equal to h. If this is approximately equal to 1, multiply everything by h, the numerator becomes approximately equal to h. I am looking for e. Remember, I don't know e, I want to make something for e, so I have to isolate e. That is my goal. Don't forget about that. To isolate e, the first step is to move minus 1 to the other side. So then it becomes e to power h is approximately 1 plus h. Now, hopefully you can answer me. E is still not isolated. I have e and I have h on top, but still I insist to isolate h. Isolate e. Can you tell me what to do now?
Root.
Yes. H root, by the way, is not meaningful because this symbol is reserved when it is this natural number. So this you cannot use, even though I understand what you mean and you are correct. So let us raise it to power 1 over h. So that's the same thing. You cannot call it h root because h is not necessarily integer. So but the idea is completely right. Oh, sorry. I would raise it to power 1 over h to isolate e, but then the right-hand side I have to do the same thing. And then finally, I have a very nice formula for approximating e. So this e to power h to power 1 over h is nothing except e is approximately 1 plus h to the power of 1 over h. So this is a good formula.
But this is when h is 0.
Not h is 0. H is 0 makes problems for me because 1 over 0 is not defined. This approximation is good if h is relatively close to 0. If you want to have a better approximation, you have to go closer to 0. But that is not bad because I can start a table like this and then I realize some digits become stable. Then it means that I can rely on those digits. So exactly like this, I will do it for you. But if you want to, you are right. If I want to write the exact value, that's also a good question. So let me just immediately answer that. If I ask you what is the exact value is the limit of that expression when h goes to 0. Very important. So I was able, by the way, if you wanted, if you don't like to use approximation, you can work with limits all the time, and then you will get this at the end. So you can start from here, multiply everything by h, and then of course you get this one. But of course that's a technical problem because h is a variable of limit. You have to make sure what you are doing is plausible. Okay, but then this formula will help me to find approximately what e is. And I have done it here, so let me just copy and paste my numbers here for you. Yes. So what I want to do, if you don't mind, let me move this up. And let me clean this here. And now fill it up with the new numbers. But which one I have to put in? That function. Function 1 plus h to the power of 1 over h. So I would write the function here, 1 plus h to the power of 1 over h. And I will choose exactly the same numbers because I want to get closer and closer to 0. And I copy and paste my calculations here. This one is 2.59, 37. This number becomes 2.7048. This number becomes 2.7169. And that number becomes 2.71 and 81. Oh, I did one more here. So the other one is 0.00001, and the answer I got is 2.71 again, and then I get 83. So at least this shows that I can rely some of them. First of all, I can really rely on 2. It's all the time stable. But 5 is not stable because later it becomes 7, but 7 seems to be stable again. And then 1 is also stable. 8 also seems to be stable. So it means that I can consider this to be an approximation. 2.718. But if I want to keep 2 decimal points, this is why people write up to 3 decimal points is 2.718, but up to 2 decimal points it is 2.772. 2.72. Okay. If you were so curious about what that kind of number is, by the way, this is very interesting. If you know a little bit of physics, you know that if you change these digits a little bit, the universe will change. So it's very interesting that these digits are exactly the digits that they are, because the constants of nature somehow rely on them. So it's important to understand that these numbers are actually very important. Your life depends on it somehow. Yes?
Is there a concept like this which is
Which is what?
which is rational?
No, I haven't seen that. Even another constant of mathematics which seems to be extremely important is the golden ratio. So some people believe, there are some, I was listening to some talk from a group of scientists in quantum gravity research group in California. I think they realized, because you know that one of the mysteries of the universe is that why the speed of light is this number, or why the electric charge of electron is exactly this number. Or, I mean, these questions are still puzzling physicists, and they realize that these speed of light can be expressed in terms of golden ratio. So then it means that probably life is more mathematical than physical. So might be mathematics behind everything. I don't know, but this is so golden ratio is also not a very strange number, but that also happens to be irrational. And the golden ratio is this number, square root of 5 plus 1 divided by 2. That's the golden ratio. So that's number denoted by Greek letter phi. But that also happens to be irrational. Okay, let us go back to the lesson. So now, hopefully, this 2.72 plays a vital role in your life. But anyway, let us go back. Let me just remind you, because it is a very big detour now. So you remember what was my goal? My goal was to start from this function and calculate its derivative. I succeeded mainly. The only problem in front of me is calculating this constant. And I realize this constant is the value for this limit. So far, I haven't succeeded to do that, but I was able to solve problem completely for one particular case. And that is the case when this when this A is E. So now, can you tell me what the answer is? Let us take this a and replace it with e. If I ask you e to power x what this is an exponential function, but this is an exponential function whose base is the Euler number. Okay, now I ask you, what is the derivative? Can you tell me? The derivative is L multiplied by the same function. So this is L multiplied by the same function. But what L is? L is the limit e to power h minus 1 over h, because in this case a is e. But what is this limit? 1. It's very, very lovely function. Yes? Because if L is 1, its derivative is itself. So the derivative of this function is itself. So I want you to understand the main problem is not solved. It's still a long journey in front of us to solve the main problem. The main problem, the original problem. We were not able to solve this problem in full detail yet, but we were able to completely solve that problem for a special case. And that is the case I want to write, and I want you to remember that. E to power x, if your function is this function, it's a lovely function. Its derivative is e to power x itself. Yes, please.
Why is it this number e? Why does that happen?
What do you mean what is happening?
No,
I try to motivate you,
Yeah,
the
exactly,
logic
but
behind that.
Why does just e specifically happen? Like why does 2.718 something happen to become its own derivative when raised to power?
You want to understand it from a deeper perspective? I don't know.
Yeah, well, I mean, is that part of like?
I mean that if your question is this, that is there any way that a priori I could see this?
Yeah.
I don't see any way to understand it before doing the calculations.
So how do you calculate e then?
No, the calculation, because my presentation is at least telling you something. You know the missing points. Okay? Because not everything I can talk about here, but at least you know which ones are not complete. So you know the gaps, but the logic is quite good. Okay? So I don't understand the question again.
Well, I just think it's like of all the numbers that happen, like there's no other number in e which becomes its own derivative when raised to power x.
By the way, you could ask this question from yourself. Is there any function whose derivative is equal to itself?
Yeah.
You can answer yes, and that's this function.
And only there's no other.
No, there are. Because you can write e to power x plus 2 as well.
Yeah.
And then e to the power of x plus 2. But as far as the derivative of the numerator is 1, this is the unique function with that property. Of course, you can multiply this function by any other number. So if I ask you what is the derivative of 5e to power x, the answer is the same. Because if I take the derivative, I told you that this is a multiplicative constant, so you don't care about it. You just care about differentiating this one and put it back. But you see that again, this will generate the same function itself. So that is not the unique function with this property. But all the functions with that property has something to do with e. So in general, this would be something like this. Any function of this form has derivative equal to itself. Not a big category of functions. It's just multiples of e to the power of x. Yes?
Function.
Yes, do you have questions?
When a function is 0, f of x equals to 0,
F of x is equal to 0 what?
wouldn't that also have to be its own derivative?
Yeah, but that's also some special case of this by choosing c equal to 0.
Yes.
Yeah.
How is this in any way useful to find the other?
No, but you have to be very patient. It comes gradually. But what we learn is that we started with a problem. We couldn't solve that problem in its full detail, but we were able to solve this problem partially by realizing that it's a very important constant in mathematics, and happens that the derivative of that function is equal to itself. This is what we have just learned, okay? So, for example, for the people who are not that interested in knowing things very deeply, You can forget about everything except the last line. So f of x equals to e to power x, the derivative is equal to itself. And there are some exercises in the book that I want you to know. For example, let me give you some examples before, don't forget, still the main problem is left. So I would say that example, differentiate the following functions. Differentiate the following functions. Okay, so for example, let me just write 1a, f of x is equal to we cannot give so many examples at this point, but let me just write one. A to the power of x plus x to the power of 2. I don't know, the examples shouldn't be that hard. Yeah, because I cannot combine them more. But it becomes interesting later, okay? Yeah. So what is the derivative of? Let me just give this one, the following function. So what is the derivative of this? It's very simple, yes? F of x, f prime of x is equal to the derivative of the first one plus the derivative of the second one. So the derivative of the first one we learned today is equal to itself, and the derivative of this one is what? x2x. Oh, okay, but let me write another one for you. G of x is x to power e plus e to power x. It's a good example because you can feel the difference in one single example. So what is the derivative of this function? E to power x plus x to power e. Or the other way around. X to power e, e to power x. I want you to feel the difference. This function is the old lesson. The only thing that is new is just introducing this number. But this is the new lesson. So if I want to differentiate this function, what do? I would write e x to power e derivative plus e to power x derivative. You don't need to write it, but I want to write all the details. This one is the old rule. E goes down, and then you write x to power e minus 1, that's it. You don't need to take your calculator and put the numbers in. But the derivative of this one is just the function itself. So that will be the answer to this function. Okay, so you might look tired, but you have to be patient a little bit so that I can finalize this lesson. I will not continue. The next lesson I will cover the rest. But there is some problem in the book. I don't like it, but because it is in your book and it will be covered in the book, what happens if I have a number multiplied by x? I don't like it because that is under the title of the chain rule that you will study later, but might be the only reason that they put k here, because if they don't put k here, the diversity of the problems vanishes immediately. So you don't know what to do. Exactly what I wanted to do, I couldn't. Whatever I want to do, I have to work with just this boring function all the time. Okay, that might be the reason. But let us try to understand this, and I want you to tell me how to do it. Before going to the main problem, okay, before going to the main problem, I want to ask another question. Answer that question, stop the lesson today, and continue next session. So my question is that, can you help me to do this one? I start with this function. Let me write g of x. You already know the answer. If g of x is e to power x, then g prime of x is e to power x. My question for you is this. If f of x is equal to e to power x, not just x, multiplied by a constant, my question is that what will the effect of this change will be in the derivative? We want to answer this question. It is not that easy that you can guess. We have to calculate. Okay, so at least you understand the question. But let me write something in front of your eyes. The limit of e to power h minus 1 over h goes to 0, is equal to 1. Remember that. Now I want to calculate the derivative of this function. C is any constant that you like. 0, 1, minus 1, square root of 2, whatever. We want to calculate this. Okay, this is a new function. What I want to do, I have to do the calculation again. So f prime of x is equal to the limit of f of x plus h minus f of x divided by h goes to 0. Yes? But what is the first part? F of x plus h, I replace x with x plus h. So this becomes e to power cx plus h minus e to power cx divided by h goes to 0. So if you want to understand, you have to be a little bit careful here. Okay, what should I do? I will take the same story here. I multiply c in. And then what I do, I decompose this as to e to power cx times e to power ch minus e to power cx divided by h goes to 0. And then I can factor e to power cx out, e to power cx, and then I have e to power ch minus 1 over h goes to 0. And then e to power cx, for the same reason, this is a constant for this limit, because this limit depends on variable h, but variable h does not appear here. So as far as this limit is concerned, this is a constant, I can pull it out. And then I face a little bit problem here. My question is that, what is your guess about this new limit? You cannot definitely say 1. Of course, you can say 1, but you have to defend yourself. Because I know this limit is 1. My question is that, is there any way to understand the value of this limit if this value is 1? This is the question. You can think until I am erasing the board. Yeah, I can erase this, but I will copy and paste it later in the coming lesson. Is there any idea how can I understand the value for this when I know the value of that? It's a trick, I haven't talked about that yet, but it's not very hard, you can understand it. No, there is no splitting.
No, it's definitely going to be bigger, or no, it's not. It's not going to be 1, because we could change that e to the power of c times h e to the power of c.
Yeah, exactly. It is, you shouldn't expect that it should be 1 again. But the point is that, let me try to understand what is the limit. I will do some changes and then I will ask you again. E to power c, the goal is to calculate this limit. Okay, do you agree with me that I can write it as c times the limit e to power ch minus 1 divided by ch, h goes to 0? Do you agree with this? That this limit can be rewritten in that way. What I did, I multiplied by c divided by c, because c is a constant, so it doesn't matter if I put it here or there, because I can pull it out. Understandable, this one? This c, if you don't like it, put c here. C and C cancel, I go back to the same thing, but C is constant, I pull it out. Yes? But now, why is good? Why this is good? Because I can call this capital H. C times H, I call it capital H, and then I continue. This little c is little c. Instead of C times H, I put capital H. Instead of CH, I put capital H minus 1. But here little h goes to 0. But what is the consequence of this for capital H? If little h goes to 0, what happens to the capital H? That goes to 0. Okay, now do you think that you know this limit? You know this limit, because that's the same thing, the name has changed. Yes? So that limit is again 1, but the price that I have to pay is this constant c. So then it becomes c times 1 again. And this becomes c. So your guess was correct. This cannot be 1 again. This becomes c.
Unless
Yes.
C is 1.
Unless c is 1.
But, okay, so in that first, what's the domain of x in this original one?
So the domain of x is always r. And that is the reason that I actually took off the negative numbers.
Okay, so
Might be I didn't mention the express. For any exponential function, a is not equal to 1, a is greater than 0. This guarantees that the domain of this function is r.
yeah,
But the range is are positive numbers.
yeah. But so in the first one, right?
Yeah?
C times x in the second one, is that not a part of that range?
No?
Why?
No, I mean that, what do you mean by the range? I mean,
Well, I mean, like, because you said,
I will talk about the graphs. The graph of a to power x are two types.
yeah,
Either I have this kind of functions,
Yeah.
so you see that the domain is the whole r, but the range is positive, or I can have this scenario. This happens if a is greater than 1. This happens if a is between 0 and 1. Okay, so then still I don't understand the question then.
so I just, because you said you multiply x by a constant c, right?
Yes?
So in this second case, and that changes the answer, but if x can be any number, like if you add, like if you
No,
have,
don't get confused. I have a different function now.
yes,
For example, if I give you the derivative of e to power x, you know it is e to power x. My question is that what is the derivative of e to power 5x?
yeah,
But if I ask you the domain of this and the domain of this are the same.
yeah, but okay, if let's say the derivative of e to the power of 5, is that e to the power of 5?
Tell me.
Yes, it's,
Do you remember in the first session? I know that this question you will ask later.
Is it 1?
Come on. E to power 5, what's the derivative? I have to give up teaching math. Because if you remember, do you remember when I was teaching the derivative of a constant,
Oh, it's
I told you it is 0, and I warned you that you will make a mistake. I wrote a lot of constant numbers at the end. Do you remember? That was anticipating that this is going to happen. And you start laughing at me. Okay, we understood, Babak, that's enough. It was not enough. Yes, because you made the same mistake.
Yeah, but
E to power 5 derivative is
0.
0 because that's a constant function. I told you it doesn't matter how you write the constant function, yes? F of x, let me just repeat that scenario again. I don't know, sine of e to power 5 plus logarithm of tangent of square root of 2. What's the derivative of this one? 0. Yes?
What does that mean then? That e to the power of x is non-derivative? How can,
No, because if that's a constant, I will have a different problem.
yeah, but if you
This is not a this is only this function. This function is not equal this function. You cannot say that this is the same function but x is 5.
yeah, but if you assign any value to x,
No, you cannot. Be careful. If I assign any value, I no longer have the function. I have the value of the function at one point.
yeah,
So e to power 5 is not the whole function, is f of 5. It's not a new function.
what is that graph of e to the power of
E
x?
to power 5, I don't know, 2.72 or something. You raise it to power 5, it becomes around 40 something, and then it becomes this line,
Yeah.
where here is approximately e to power 5,
Yeah, but what does the graph of e to the power of x look like?
like this.
Yeah.
No, you are getting confused. You need to rethink about, these are not the same thing. There is no way. So if you tell me how you interpret, so if I give you f of x is equal to e to power x, e to power 5 for me is f of 5. But if you insist to write this as a function, I agree with you, but this function is not this function at all. Coincidentally, the value of this function at one single point matches with the value of this function.
I'm getting confused.
Yes, you're confused. So this is a good sign that I have to stop. Okay, but the point is that let me complete that one. So this limit, this trick is nice to learn. So then you get C. So what happens? Let me answer the question here. Okay, now can you tell me what happens here? So if I put that back here, do you remember? I started from the derivative, I reached up to here. My question was how to calculate this limit. Hopefully I was able to convince you that limit is C. I put it back in this equation, so it becomes e to power cx multiplied by c. So then I would write this, and I promise I will end here. Okay, so this is the new formula. So if I have e to power x, the derivative is exactly the same function. But if I have e to power a constant times x, the derivative is still the same function, but the constant also goes down. Okay, so if you don't mind, let us keep the lesson just right here. Even though it's not a good stopping point, it would be better if I give you more examples, but let us stop here. I will try to recap a little bit later and then come back to this. But remember at least one thing, the main problem is still not even partially solved. Yes, because we want to understand this, and this gives rise to a new kind of logarithm, which is called natural logarithm. And this is extremely important. So you know a little bit about logarithm. So if you want to do something until the next session, review a little bit about properties of logarithms. Any questions? You have to be prepared a little bit for more 2 sessions. This is life. Yes? Yeah.
So what will be, so we say that we have a function f of x equals to c times e to the power of what is it, ax. Then the differentiation or the derivative of that function is equal to, it is equal to ac times
Yes.
e.
AC to power ax. Yes? Yes? Okay. Thank you very much.
Maybe I need to